Our next speaker is Laura Fissing from Cambridge as well, and so she will talk to us about a stable learning framework.
Yes, thank you very much. So I will talk about stability, as we've seen already today a bit. And so the way I want to talk about it is that I first also going to talk a bit about adversarial examples, but I keep it short as we all kind of familiar with that. Then I would like to remind you of the PAC learning system and the learning setting, and also discuss some of its shortcomings to then finalize it with some framework which we might be able to use to get into the direction of more stable networks. Okay, so I guess that's the most popular one. So we have this very tiny perturbation, and the left-hand side is classified correctly, and on the right-hand side everything is said to be an ostrich. And I think for none of you can see any difference between those two images. So this is quite a bit of a problem. Then there are also other types. If you have some images which are completely unrecognizable, which look pretty much like white noise or some other kind of pattern, they also get classified with very high confidence by most networks. And then one of my personal favorites are the geometric transformations, which then also lead to misclassification. And because if you imagine, if you take a picture with your camera and you just turn the angle, so this can kind of easily happen. And as we've seen in the two talks before, this is not something which just happens for classification, even though I want to focus now on classification, but also in inverse problems, in spam detection, speak recognition, and I guess in most applications where people are using neural networks. And so I think one of the big questions we have is what is actually stable learnable? And therefore I think as mathematicians it would be great if we have maybe some framework where we can build this on. And for that I will now first gonna get us together with the same notation, because I sometimes feel it gets a bit mixed up and then it's difficult to follow. So what we have is we have a certain training set, which I denote with xtrain with m elements, and with the according labels, which I denote with y, and they're labeled with a certain function f, which I call either the labeling function or the concept. Then we have a certain set of hypotheses or possible functions, which we denote h, which in most applications nowadays are neural networks. And then we take a loss function, which takes in our training set, our labels, and our hypothesis class, and then tries to give you some kind of approximation on the accuracy of your network. And if you have all that, you can take a machine learning algorithm, put in your training set and your labels, and you get out some kind of minimizer h star, which is then minimizing the loss function. So I think that's probably familiar with everyone. And the system has been around already a bit longer. And so what's a very nice framework is by Bayesian, which is called the probably approximately correct learning system. So in the following I will just say PAC learning. And so this really, really nice framework, which focuses mainly on the number of necessary samples, so we get an idea of the complexity. It also tells you something on how to choose your hypothesis class to get in with the bias and the variance trade-off. It works for any kind of distribution of your underlying training set, and it is focusing also mainly on the probability of the accuracy. And so it's a very nice framework, but it also has quite some shortcomings. So the main is that it doesn't focus on the stability of h star. And as we've already seen today, this is a really big issue. There is some research, so therefore I just say that, on the stability of A on the algorithm. So if you take your training set and replace elements out of your training set, but that's not what I want to talk today about. It's the stability of h star, just not to get the two parts of the research confused. And another one is that it does not take the concept class into account. So the function we use for labeling isn't taken into account in the PAC learning system. And I think it's very important that we think about it what actually do we want to approximate? Because there might be just questions which are not reasonable to ask a network about an image. If you imagine there's a kid on an image and you ask, does this kid like strawberry ice cream? And you were like, I don't know. As long as this kid isn't eating strawberry ice cream and laughing heavily, you probably just don't know. So you maybe want to consider what kind of questions you want to ask your network. And then your adversarial examples, as we've seen, there are tons of different types. They usually also don't lie in your distribution necessarily. So if we have accuracy on a certain distribution, that doesn't really tell us that our network is indeed stable. So that's another problem. And it tries to solve this now for any kind of distribution. But that might be just a bit too much, because it's okay if we just want to approximate a function on like natural images, and not on just any kind of distribution. If there's a distribution which favors Gaussian noise, probably most people are not really interested in finding out something about Gaussian noise. Or maybe they are, but not in this setting. So therefore, it's also reasonable to focus yourself down a bit on the distribution side. And so it's not just me being concerned, that's probably all of you actually. And also you see that in the sciences and in the media, where we've seen this morning with Anders that also in medical care there's already like some fraud between practitioners and insurance, and if you now introduce machine learning on top of that, it just makes it even worse. So it's getting even more difficult like to distinguish if this is like really a necessary treatment or not. And so yeah, this big issue also for driverless cars, if you have like some of perturbations which are then even another type, even looking different, and which make your stop sign being like, say, go fast, it's like maybe not what you want if you sit in the car, or even worse, stand in front of that car. And I found a really nice quote out there, which I think is funny, because which says that people worry that computers will get too smart and take over the world, but the real problem is that they're too stupid and have already taken over the world. So yeah, so I think, yeah, everybody's pretty much aware that this is a big thing. Okay, so the questions we're interested in is which questions are actually solvable with neural networks. So as I said, we really should be considering our labeling function f. How can we make sure in practice that we indeed find something, that our algorithm gives us something that is then stable? And related to that, can we make them then really stable against adversarial attacks, especially against any kind of adversarial attacks? That's like even a larger question. And how do we actually want to measure performance? So what's performance? And I think accuracy is very important, but we need to take both into account, accuracy and stability. Because if we now just go for stability, if you take a constant function, that's perfectly stable, but that's also not really helping you for anything. So it's important that we now like open our minds and take both sides into account. And there, as we've already seen this morning, there's quite a bit of work in this direction, and I just want to repeat a few things of that. So there are tons of different kind of attacks. So like the invisible changes we've seen, you can also make changes that give you the target class, so you can decide what the network is supposed to tell you as a wrong answer. And you can make geometric changes. You can also have black box attacks, so you don't need to know your network by heart, but you can transfer them, which relates then to the final point, the universal perturbations. And a lot of people are trying to work hard, and it's really interesting to see, like this morning, the work on the adversarial training, which definitely highly improves already the quality. Or like data augmentation, and also constraints on the Jacobian or the Lipschitz constant, or as I've now also learned on the Hessian matrix. You could do some distillation. You could also use other regularizers, which is all very great because it all improves the quality. But yet, as we've seen, we are now from 0 to 50%, which is great, but the 50% is still not 100%. So we're still like somewhat in a bubble. And therefore, I would like to introduce now the framework, so that we maybe find from our mathematical point of view some underpinning for getting this work further. And therefore, I would like to remind you again on notation. So we have this set of concepts F, which are the concepts or labeling functions. Like if you're, like for example, if there's a cat in the image, like the classic. And then we have the possible functions H, which are then usually neural networks with a predefined architecture, which you decide before you start your training process. And then you have an algorithm H, which then gives you, depending on your training set, your minimizer H star. Okay, and as I've now said before, we want to have that the underlying function F is already, like our labeling function is reasonable. And what we want is that it's epsilon F, delta F well conditioned. So what that means is if you have some kind of distribution where you assume your data is on, you take points and then you have an epsilon H ball in a distribution where you, in a ball with a norm, where you're now very flexible on choosing what kind of attacks you want to be safe against. So you can go for L2, L infinity, or whatever you like feel like is the most important bit. And then, because we want to focus now like just on binary functions, because you can easily go from binary functions to multi-class functions, that this function is then constant on this ball. And to like, maybe you're in a situation where security isn't super important, and you say, I can have like a small delta area where I'm fine with adversarial perturbations, where it's not constant. That's okay for my application. That you can decide on with delta F how often it is allowed to happen or not to happen. Okay, and if you then have like a well-conditioned question to start with, so if your problem is then somewhat well-conditioned, your learning problem, you can then go and have an S epsilon S delta stable learnable problem or hypothesis class. And because we want to keep it in the light of the PAC learning setting, we also include the function MH, which regulates you the number of samples that you should take in, because obviously that is part of the problem that you need enough data and you also want to have a bit of a handle on that. And then your algorithm is said to be has that epsilon H and epsilon F are related with S epsilon, and delta H and S delta are related with delta F. Delta H is related to delta F with S delta. And then also your H functions, which you are getting out from your algorithm, is supposed to fulfill the same assumption with the slightly different balls. So we also want that now that the function that we're getting from our algorithm is indeed constant on this balls, related only on how much you can expect it to be constant from your labeling function. And also there you can allow for a certain uncertainty if you want to. Okay, and just like a very short reminder that this is like not directly like, maybe you feel like, okay, we have the universal approximation theorem, so we can approximate smooth functions. Isn't like, because it always pops up easily in your mind. You feel like, oh yeah, with that we're kind of solved. But this also shows you that if your underlying labeling function isn't smooth, then this won't help you. And also another type of concern we usually have with this is that you need to fix your number of neurons in advance. So it's also usually in applications difficult to get that indeed through. And with this, we are still in this open question that which, if neural networks can indeed do classification in a stable manner. And I think, I hope this opens up a bit the idea of where we might want to go and where we might want to keep our focus on. And with that, I will show you a bit of literature and I would like to thank you for your attention.
Yes.
I noticed nobody today has mentioned Bayesian networks, and I just wondered what your thoughts are on, so if you're estimating sort of posterior over the weights rather than point estimate, how that might help with stability.
I haven't really thought into that direction, to be honest, so I'm more of a
posterior over the weight space might be multimodal, for example, and so if you're just doing a point estimate,
yeah,
you're always in a different sort of, you know less about the weights with regards to the training data than if you're taking that Bayesian approach, because it's obviously more expensive as well.
So you mean if you take further assumptions on how your weights are distributed?
Yeah. So there are people working on Bayesian.
Yeah.
Bayesian estimation of the weight space, and that sort of feels like in the mathematical community the most natural to me.
Yes.
Folks that wanted to take it. I'm sort of surprised not to hear about it today.
Yeah, that's indeed surprising then. But I actually also haven't really heard about. I haven't really read into that, but I would be very happy if we could have maybe later on in chat, and you could tell me a bit more about it, so that
Sure.
I can broaden my horizon a bit.
Anything else? So I had a question about your so you mentioned a completeness result at the end. How was it related to the previous talk? There was a completeness result also in the previous talk about the row not being a polynomial and so on. And you had two
yeah. Yeah, so
this one, yeah, and there was a completeness result in his talk. Is it the same?
Yeah,
it's a two-layer network.
Yeah, it's the same. It's the same theorem, at least as I'm concerned.
Okay. Because this assumption of a non-polynomial row function is not here.
Yes, yeah, I just shortened it up because of the 15 minutes. I thought it's easier if I just keep it to the, to the main idea of it. But yeah, the full version we've seen before.
Any questions? No? Okay, so let's thank Laura.